let's just summarize quickly what we have been doing in the last couple of lectures in order not to lose the direction. One important result that we obtained, this is important because we did not use any decayed Lagrangian or equations of motion, was spectral representation. Spectral representation of the two-point function. So we showed that in the Fourier space, this function, if we use bare fields, has the structural constant times I divided by p squared minus n squared plus I epsilon plus an integral from a lower bound, which is bigger than m squared, over a variable capital M squared times a function sigma m squared times terms like this, but the small m squared replaced by the capital M squared. This result is important because it gives us sort of information about the two-point function, one of the key elements in quantum field theory, without making use of the detailed form of the interaction Lagrangian or even the detailed form of any Lagrangian. So this scalar field, for example, could be coupled to other things, other fields, could be coupled to fermions, etc. Still, you could derive this relation. The only thing that we used was the Poincare invariance of the relativistic field theory, nothing more than that. We made a couple of assumptions. The assumption was that the ground state expectation value of the field was 0. If it is not 0, then we can always add to it a constant and make it to vanish. And this is not an assumption. I mean, we made assumption about the structure of the eigenstates of the for momentum, energy and three-dimensional components of the momentum. And for the single particle states, that means single particle state means the lowest energy state above the ground state. Okay? This is the single particle state. Essentially, Lorentz invariance tells us that this should be of this form. The Z is introduced at this stage. This is the same Z which enters there. And then we argued that if we replace this phi hat simply by a simple rescaling, obviously on the right hand side then this Z will be absent. Okay? For phi, for this one, in that case we denote this by a renormalized P. The residue at the pole is I instead of Z, or I times Z. So at this value of m squared, there is only a simple pole here. And since this m squared is the eigenvalue of p hat squared, the momentum operator squared, therefore it's its lowest eigenvalue about 0. We have assumed that the momentum of the ground state is 0. Therefore, we can identify as the mass squared of the lowest state in the problem. Okay? Any questions so far?
And then integral, why did you take m squared to be a continuous variable?
It turned out to be a continuous variable. The way that we formulated it, derived it, it automatically turned out to be a continuous. It was just introducing a delta function, rewriting something delta function. It was just m squared was a continuous variable. This was introduced by introducing a delta function to write this sigma of q squared or something as an integral over sigma squared. The idea was to reproduce this term. The guiding principle was that we wanted to write the exact 2-point function as a superposition of the 2-point functions of free field theory. Okay? But with different masses. So the leading term is the free field theory with the lowest possible eigenvalue of p squared involved in ground state, and the subleading terms are precisely the same form, but superimposed. It means there's a superposition. There's a sum over them with a density, which depends on m squared. This was the guiding principle. That's where we wanted to end up. Okay? Ultimately, it is related with our assumption about the structure of the states, eigenstates of the momentum operator. Other question? Good. Now, here we stop discussing the generality and go back to our toy model.
I have one question. Inside the second line where you manipulated.
This one?
No, below that, this one. So suppose that you have a spinner, then it will have a non-trivial transformation.
That's right. So if you have a spinner, then the right-hand side should have the same transformation property as the field entering there. Mm-hmm. Right? Therefore, that spinor wave function should enter there.
Okay.
So the Lorentz transformation property of the two sides should match each other. So let's go back to the model. This is just a model I've chosen because I wanted to exhibit in a one loop graph the wave function renormalization, this Z. Okay? And this in 4 dimensions, 6 dimensions is the model that we are studying, namely a scalar field theory with phi cubed interaction. So the starting model was written in terms of the Bayer fields and the Bayer mass and Bayer coupling. We said that this shift, if the ground state expectation value of phi hat is different from 0, we can always shift it by a constant, and that happens here, and it produces a term we can call G0 phi, a linear term. Now, making substitution, writing phi, the Bayer phi in terms of the renormalized phi, I'm dropping the subscripts r, etc. from here. And also the mass, m0 squared is a parameter of dimension of mass. It can always be written in terms of the physical mass plus some difference. These are two parameters with dimension of mass. The difference we are writing, well, the difference, okay, let me go step by step. And these are trivial steps, but maybe you should see it at least once. I explained this somewhat last time. Maybe it was too fast, so I'm going quite slowly here. I just replaced phi by z times phi. Okay? Now you see that here there is a one more step. We argued last time, I think we did this. Last time we argued that this z for the free field is also obvious. For the free field, this z will be 1. Okay? What we want to do is to develop a perturbation theory in terms of the renormalized field. So in any field theory, to develop perturbation theory, you have to write the Lagrangian or the action as a free part plus the interaction parts. The free part is always the part that you know how to solve. Solving means, for example, that you know how to diagonalize a Hamiltonian or how to solve equations of motion. Okay? This is the meaning of solving a quantum field theory. How to find, if you know the complete eigenstates of the Hamiltonian, then essentially you have solved. The free part is identified as the part which you know how to solve it. So usually in this kind of problems, the free part is 1/2 phi minus t squared minus m squared times phi. That's the free part. But here we have in front, we have a z. So we are going to write this z as 1 plus another constant a. Eventually all these constants will turn out to be functions of physical parameters. Okay? Now if you do that, then the one part coming from here will produce 1/2 phi times this operator times phi. The one piece from here. And that will define us the free action. Okay? So the action then, the leading term, the first term, will be 1/2 phi minus d squared minus m0 squared phi. And I'm going to write m0 squared also as m squared plus something else. This something else I will identify in a minute. So the m squared also will go there so that the free part will be written in terms of the renormalized field and renormalized mass. If you substitute here m0 squared, m squared plus something else, I'm just picking up the m squared part here. That something else will go into the rest of the arrangement. Okay? So the rest, whatever it is, the constants coming from here and coming this other things, I'm going to call it b times delta m squared. So there will be here from the rest, there will be a 1/2 b times delta m squared. Well, b times m squared. So this thing, put all the constants together, multiplied by this, etc., whatever comes out, just call it b times m squared. Whatever comes out will have the dimension of mass, mass squared. So this m squared is that mass squared, and the remaining constant I'm just dumping in this b. Okay?
So we know that this term has to be proportional to m squared, because if m naught is 0, then m squared has to be 0 as well.
Yeah, I mean, it's a parameter of dimension mass. I can always call it some constant times m squared. But you can find various reasons for that. Then, okay. This 1 plus a is going also to be inserted here. So what we want to do, we want to replace also this lambda 0 in terms of renormalized constant. It's just redefinition of the parameters. You have a question?
Isn't there like phi squared or something?
Sorry?
And the new term that you wrote, 1/2 b m squared.
Yeah, phi squared, yes. So here, again, I'm going to just redefine the parameters and rewrite it in the following form. So this whole term will be written, that means lambda 0 z to the power 3/2. After we substitute for z, etc., will be parameterized as a coupling lambda again, a point about the remark about dimensionality. This lambda 0 in n dimensions will have a mass dimension. So we want to write in terms of a parameter which is dimensionless. Therefore, we introduce a parameter of dimension mass, which takes care of the mass dimension of lambda 0. Z is dimensionless. Okay, it is the ratio of two fields. Therefore, it's just a constant dimensionless. And this dimension is in n dimensions. That's minus n over 2 plus 3. That's one part of it, because we know that. Well, okay, that's one part of it, plus the so-called counter term. The counter term is, I parameterized last time by C times the same mass dimension times lambda. So it is the renormalization constant is the C. And likewise for this last term. This one. So anyway, putting everything together, and quickly run out of space on this blackboard. Maybe I'm not using it properly. So I should have written it here, perhaps. So what we want to do is lambda 0 times z to the power 3 half. We said we want to write it as minus n over 2 plus 3 plus, plus c times the same times lambda. You see, this is not an essential point putting this term here. It's essential if you go away from 4 dimensions and if parameter as mass dimension. And especially if you want to use dimension regularization. If you want to use a cutoff, for instance, you could leave it just lambda without that term. Okay? It is not that this is not a key point at this stage. It will play some important role later on, but at this stage it is not a key point. The important thing is that we are writing this lambda, or lambda 0 times z, as a renormalized coupling plus extra terms. These extra terms are called counter terms. As a result, when you multiply it by phi cube, there will be a term like the original term in action, modulo this extra mass dimension, some power of mass, plus the contribution coming from the counter term, or minus c over lambda over 3 factorials, c times mu minus n over 2 plus 3 times phi cubed. Okay? Then there is this new, the linear term. I'm just going to call it G5. So what you should keep in mind is the number of parameters of the problem and the number of constants that you have introduced. The constants are not new parameters. This A, B, C, what happened to A? There is also this A, I forgot to write it. A times this term should also stand in here. So we produce a lot of terms from the action which had a smaller number of terms, basically three blocks. We produce an action which has more terms in it. Okay? Any question on this? It's just rewriting. It's nothing more than rewriting at this stage. But there is a reason for this rewriting. The reason is that now we have a part which defines the free, non-interacting part of the model with the physical mass in it. Okay? And then other terms, we know that the other terms should start at least with the first part of the coupling constant lambda. Therefore, we can dump all of them in the interaction part of the Lagrangian. So the interaction part of the Lagrangian consists of two parts. One is this part, which is like the original term with the coupling constant replaced by lambda instead of lambda 0. Then all the remaining terms, this one, and this, they have the so-called renormalization constants in them, B, A, and C. Okay? However, we know that these renormalization constants also should start with some power of lambda, therefore they should also be part of the interaction Lagrangian. So as in every perturbative approach to quantum field theory, the first thing you do is to write down the Feynman rules starting from the action. Now, Feynman rules, the bilinear part always gives you the propagator. The propagator is the inverse of this operator with I epsilon added to the denominator. And then there are the interaction vertices. Interaction vertices come from the remaining part, which are the part of the interaction Lagrangian. The first one is this one, which is like the original model. It's a 3-point vertex, and we know that in momentum space we should associate with it I lambda. I have put this factor there, so that's this part. And then there is another 3-point vertex because there is phi cube term, but the coefficient which is different from that one. And in order to distinguish them, I will put a little field sphere there, small or large dot. And again, following the Feynman rules, it's precisely the same thing except that it has a C in addition to lambda. But there are other terms as well. There is this term and this term. Both of them contain phi squared, phi, and phi squared here. Therefore, we are just going to write them together. And if you go to the Fourier space, you can read what you should substitute. This minus t squared goes simply to p squared, and that vertex gives you, you are going to represent it like this, and the algebraic expression associated with that will be I times a times p squared minus n squared plus I times p times n squared. Okay? Having the Feynman rules, you can start calculating whatever you want to calculate. So the first thing we want to calculate is to go back to this 2-point function and calculate after the one loop order, then impose the renormalization conditions to fix the renormalization constants as we described last time. Any questions? So let's then start calculating. We don't need any of these parts. This model is not a good model, it's phi cube, because its potential is not bounded from below. But as far as the perturbation theory is concerned, that's okay for what we want to discuss. Okay? So let's then look at the 2-point function, this time calculated using the renormalized quantities. But it will be easy because the calculation actually we have done before. So G2 will be the 3-level graph plus 1 loop graph plus the contributions coming from the counter term. Now we have to take into account also contribution coming from here. This part we denote again as minus I pi. The difference is that this pi will be expressed in terms of not the bare objects as before, not m0 squared and lambda 0 squared, lambda 0, but the physical mass and the renormalized coupling lambda. So if you write the expressions, this is just a Feynman propagator. Then from here to here, there are two Feynman propagators, one on this side, another on this side. Therefore, I'm going to put the Feynman propagator outside and open. Well, let me write them separately. I wanted to factorize the Feynman propagators, but let me first write them separately. So you see what goes inside here. Okay, this part we have already calculated. They calculated with the Baire theory, but the loop integral is the same. No? It's identical. Therefore, it will be the same expression, except that for the parameter you should use lambda instead of lambda 0, and for the mass we should use m squared instead of m0 squared. So that expression we can copy from there. In fact, it's in the notes, but I don't want to copy it. There is no point in writing it explicitly unless we want to do something with it. So instead of doing that, what I would like to do is to introduce, you see that we can factor out this delta F from both sides of this part and this part. Just put them outside and introduce in between a notation pi star of, these are functions of p squared, you know? Sometimes I write p squared and sometimes I write just p, which is pi of p squared plus, if I change the sign, this should be a times p squared minus m squared minus p.
I have a question.
What?
A question. Why didn't we consider the last?
The G5?
No. I mean the last one. The last diagram.
Where do you want to consider this? You can consider it here, but it will make higher order correction. I mean, it will contribute to the correction, the one loop correction of the vertex. Here, if you make it, this is already of the order of lambda squared. The C will start with lambda. So if you insert that term, it will make a correction of higher order. So if we define this, then G2P will be delta FP pi star P squared delta FP. All of these extra terms will be just put together and define a new pi. Okay? This is precisely similar to the one loop expression we had in the Baire theory. And starting from this point, we sum a set of infinite number of graphs. And eventually, after summing the infinite number of graphs, we ended up with a compact formula for the two-point function. So, sum the geometrical series as we did for the Baire theory or Baire field. And this will give us the same formula or the same formula properly doctored except that m0 squared will be replaced by m squared, and pi will be replaced by pi star p squared. We will solve precisely the same objects.
There's a missing factor of I. No, in that there.
So this should be okay.
Here.
Yeah?
No, here.
Ah, yes, minus I, yes. Thank you. To be consistent with the previous notations, this will be minus I. Yes, thank you.
And it seems like it should be minus A and plus B.
So this is pi star is defined by minus I times pi star is defined by this plus these terms. Therefore, if you multiply with minus,
You're missing a
there must be m squared there, and this is minus plus. I don't know why this is messed up. I'm not being so good as typing tech.
I think because in the notes the definition of m0 squared is like m squared plus not minus.
Okay, let's just leave it. I will correct them and give you correct. In fact, I had corrected this already, the typos of the last time, but obviously I haven't done it. I still need to do some more. Fine. Now what you want to do is start from here, in which this pi star contains the renormalization constants, to impose the renormalization conditions. Okay? So, renormalization conditions. Namely, there should be a pole at p squared equals to m squared. The first condition is that pole at p squared equals to m squared. At p squared equals to m squared, this will vanish. This means that at p squared to m squared, this term also should vanish. So this implies that pi star at p squared equals to m squared should be 0. There's, of course, we should not hide the other parameters. So in order to be clear, that is on what pi star depends. So going back to the definition of pi star, you see that at p squared to m equals to m squared, this term will go away. That we want to be 0. Therefore, this will tell you the value of the bm squared. So this tells you that the value of bm squared should be minus pi of p squared equals to m squared, and lambda. In order to be clear about the notation, I should have been a little more detailed here. This pi star is a function of p squared, m squared, and lambda. Okay? So after you have calculated this in one loop, for example, in the one loop order, take p squared and replace it equals to m squared. That will give you the constant p. Remember that we are using a regularization scheme. Therefore, this function, as long as we have not come to 6 dimensions or 4 dimensions, the function is completely verified. It will have the regularization parameter, which we call eta, for 6 minus n. Okay? But as long as that eta is different from 0, that will be a well-defined function, and therefore this will be a well-defined quantity. Okay? The second condition was that second renormalization condition was residue at the pole equals to I using renormalized field. Now the residue of this function at the pole can be evaluated easily. Okay? So in order to just match to what we did last time, if you expand pi star of p squared in a power series in, I need more space. So the residue, in order to obtain the residue, also erase pi star. There was a pi to start with. So what we do, let me first write it here. We have this function. Expand this as a Taylor series expansion around p squared equals to m squared plus higher powers. So if you make the substitution in here, you see that this is the term which is going to contribute to the residue. It is like p squared minus m squared. So you just factor out the p squared minus m squared. So G2 goes like I divided by p squared minus m squared. The first term gives you 1, and the second term gives minus p squared m squared times pi prime p squared equals m squared lambda plus higher powers of p squared minus m squared. But the higher powers do not contribute to the residue. I'm sorry. Yeah, I put this as the common factor. Plus the counter term, of course. There will be also the contribution coming from the A part, because A was also multiplied the same factor. So pi squared, p, let me write it again here. I erased it too quickly. Up to the size that this was pi star p. You know? It started with pi plus the counter terms. So what we are identifying is the coefficient of p squared minus m squared after we have expanded this in the power series of p squared minus m squared. Okay? So there will be contribution. There will be this term itself that contributes 1. There will be contribution coming from that term in its expansion. That will be p squared minus m squared times this, plus other terms. Then there will be this A, which will contribute to p squared minus m squared. Okay? Am I clear? I can erase and do it again if this is not clear. So this we want this to go like that means only this one piece should remain. And that will fix you the value of A, because If it's going to go like this, it should be 1 times that, and the rest should disappear. All the higher powers here, p squared minus m squared squared, will be just 0 as p squared becomes equal to m squared. The only thing which will survive is just the first derivative of pi. It will tell you that a should be equal to pi prime, p squared, evaluate that p squared equals to m squared lambda. So in this way, we fix both p and pm squared, that's the value of the pi squared evaluated as m squared, and a, which is given by the value of the first derivative of pi at p squared equals to m squared. Okay? This is telling us that if you go back here and substitute for a and b, pi star will be pi of p squared, and I think the sign of this was minus, as you can see here, minus, put the value for p here and write it here, pi of p squared equals to m squared lambda, and put the value of a. A is again minus pi prime minus p squared minus m squared times p squared minus m squared times pi prime. Evaluate that p squared equals to m squared and lambda. In other words, here in the denominator, we have to replace this pi star by this expression. So eventually our procedure or renormalization conditions is telling us that evaluate this pi, this loop, to any order you can, and subtract from it. So the bottom line is this: the renormalized Green's function is given by subtracting from this pi its value evaluated at the physical mass minus the first two terms in its Taylor expansion around p squared equals to m squared, around m squared. These two terms come from substituting the value of the renormalization constants, which we obtained by imposing renormalization conditions. Okay? So usually the word subtraction appears repeatedly in this business. We are subtracting something from something. The same thing will happen also when we go to the renormalization of the coupling constant. Again, we will subtract something from something. The subtraction is here. That's precisely the point where it enters. And there are different ways of seeing it. Last time we evaluated similar quantity using the pair objects. And we said that in order to reproduce the result which we obtained from the spectral representation of the two-point function, we have to subtract from pi its value at the renormalized mass, as well as pi squared minus m squared times its first derivative at the renormalized mass. The claim is that if you do this at every order in perturbation theory, the final result will be finite when the regulator goes to whatever it should go. In the case of dimension regularization, the regulator is eta, it goes to 0 in order to land in 6 dimensions. If you introduce a cutoff, the regulator will be lambda and it should go to infinity. Then this result will be independent of lambda, the capital lambda, the cutoff. Huh? You remember that one way of regulating these integrals was to introduce a momentum space cutoff. I think I gave you an exercise to calculate those integrals. So all these functions that you are calculating will depend on the cutoff. The loop that you are calculating, of course, will diverge, so you have to put a cutoff or dimension regularization. These functions will depend on the cutoff. Here it will depend also on eta. I'm not exhibiting it because it's too long, but eta will enter here. So when you make the subtraction, the eta dependence will disappear altogether at every order of perturbation theory. Therefore, eta going to 0 will not produce a divergence. An exercise for you is to take the one loop expression for pi and evaluate A, B at the one loop order and show that this pi star remains finite after you have made these subtractions. That means evaluate the pi star, which is this difference basically, and show that eta dependence at the one loop order disappears from it if you make these two subtractions. Or if you choose A and B in this way, in the way that we chose them. Okay. Is the exercise clear? Any questions? So let's go to the vertex correction. That means lambda 0. Lambda 0 and lambda. If you haven't done such calculations before, it's strongly recommended to go through the details of the exercise and check all the steps in order to have some confidence in it.
Can we say that the 3 terms in that bracket, the last bracket, the terms can be infinite individually, but this combination is finite?
Yeah, it is a combination from which the. So if you want to see the details, of course you have to do the calculation yourself. But this term, this subtraction, subtracts the, in fact maybe I should spend some more time on it. Okay, thank you. Let me go back. And essentially I'm giving you part of the solution of the problem. But in order to do that, I have to write this expression. I think maybe I should do that. So after you do, we have done this in detail anyway. We did the dimension regularization, then we ended up with the gamma functions. Gamma function is divergent when dimension goes to 6. We introduced the parameter eta, which was 6 minus n, and then expanded everything in powers of beta, and eventually we end up, after we do all that calculation, we end up with this expression. I'm writing it in compact form, but the main message should be clear. In fact, when we were writing the Baire calculation, we separated these terms from each other. This x is the Feynman parameter, which we are integrating between 0 and 1. this is the step which I was going to leave to you, but I think I should maybe explain a few more things. So it's a long expression, okay? The different terms in it are different in several respects. First of all, there's a piece in it which does not depend on eta. So obviously this piece, as eta goes to 0, will remain the same. It will not diverge because it doesn't depend on eta. The divergent terms are contained only where you have 1 over eta times something. There is 1 over eta times this expression. So the divergent piece divergent part is some number times 1 over eta times m squared plus some other number times 1 over eta times p squared. This is the structure of the divergent part. If you use cutoff, the detailed form of these things will change. But what will not change, and this is a crucial point, is that there will be a divergent piece proportional to m squared, and there's another divergent piece proportional to p squared. That means the divergent piece in this model and in all the models which are called renormalizable, we will tell you, we will see later on how they are characterized. The divergent part in the so-called renormalizable models will be always polynomial in p squared. There's a polynomial in p squared. There's a p squared, and then there's a constant. What's the meaning of polynomial in p squared? Is constant plus first power of p, second power of p squared, etc., etc. Right? It's the meaning of polynomial. This is the constant piece. This is the first order polynomial in p squared. Okay? This is the reason why, by introducing counter term which is proportional to m squared and the counter term which is proportional to Laplacian acting on phi, you can remove the divergences. Because when you go to the Fourier space, the Laplacian acting on phi becomes precisely this p squared part. The mass times phi squared is precisely this piece. Okay? Now, the renormalization counter terms also had precisely the same structure. So, renormalization counter terms also had the structure of a constant times m squared plus a constant times p squared. The way we had written it was we have rearranged these things. Let me call this b prime and a prime. In our form, the way we wrote it was b m squared plus a times p squared minus m squared. But you can dump this a times m squared with this term and call it b prime. Okay? So the relation with this general structure is that in the form that we have written it, take a times m squared, put it together with this, and call it b prime, and then there will be a times this p squared. Okay? The important thing is that the structure of the counter terms, which come from b m squared times phi squared, and the Laplacian acting on phi squared, Laplace phi, Laplacian phi, has precisely the same structure. These terms come from there in the action. Okay? That means that the counter terms in the renormalizable theories are polynomials in the fields and their derivatives. For polynomials of finite order in the fields, and the polynomial by definition is a finite order expression. Okay? A polynomial of degree something in the fields and their derivatives. This is the key point for the model, for the renormalizability of the model. Why it is so? Because then, I mean, why is it a good thing? It's a good thing because you saw that we fix the value of A and B by imposing some conditions. In this case, we needed to impose only two conditions. If you have a model in which there are infinite number of divergent terms, then you would need to have infinite number of counter terms in order to eliminate the divergences. Therefore, you would need to impose infinite number of conditions. And the model would lose its predictability in comparison with the model in which you have a finite number of divergent terms and you would need finite number of renormalization conditions. Okay? This is why the renormalizable theories are preferred. You can always, in any field theory, you can put a cutoff and make it finite as long as the cutoff is finite. And you can also make predictions. This is non-relativistic physics is full of this. Solid-state physics has the last spacing. That's the cutoff. Okay? So you can always put something analog to lattice spacing and make calculations and make some assumption about that lattice spacing. In the atomic physics, in solid-state physics, you say that it should be of the order of interatomic distance. There is a physics which tells you how large that cutoff should be. In high energy physics, it's a little bit difficult to say what is that cutoff. I mean, okay, if you are a phenomenologist, you can say that the cutoff is the highest energy we have reached, maybe something higher than that. We don't know the physics beyond the highest energy that we have reached anyway. Everything beyond that is speculation. Of course, very rich speculation. That's the content of theoretical physics, but it is speculation. We do not have any experimental handle on physics beyond the energy which is reached at LHC, or the energies that we can speculate in cosmology at the very early stages of the life of the universe.
What about Planck mass?
Yeah, Planck mass, we don't know what's, I mean, far below Planck mass we do not know anything. Planck mass could be the ultimate cutoff. Don't know. In the renormalizable theories, the important fact is that you do not need to know what the cutoff is. You can make predictions simply, essentially, by assuming that the cutoff is infinite. Because there are a finite number of parameters which you can adjust or you can play with, which absorbs the infinities of the problem, and therefore you can make meaningful predictions, measurable predictions, finite numbers. Okay? This is the heart of the renormalization program. The standard model is renormalizable. The model of leptons and hadrons and non-abelian engagements, etc. It's a renormalizable model, therefore you can absorb all the infinities by redefining a finite number of parameters. Of course, the number of parameters that you have defined is not just m squared and 1m squared and one coupling, because there are plenty of things there in the standard model. So you have to renormalize a lot of things. But nevertheless, it's finite number of renormalization conditions that you have to impose, not infinite numbers. On the other hand, if you took the same model and added in 6th dimension, for instance, in 6th dimension it's renormalizable. But if you added a term of some 526 in 6th dimension, then it wouldn't be renormalizable. We will discuss this later on. So that's the reason why we stopped at phi cubed. Or if you added higher derivatives of phi, it will not be renormalizable. You will see that at each order of perturbation theory, you generate new divergences. And for them, you would need to introduce new counterterms in action. In this way, you will end up with infinite number of counterterms, and eventually infinite number of renormalization conditions. Any questions?
Is there any difference between having a finite number of divergent diagrams and finite number of divergent amplitudes?
The amplitudes eventually are calculated using the diagrams. In perturbation, we're talking about perturbation theory. Right? Beyond perturbation theory, I don't know.
So I'm saying that if a perturbation theory has a finite number of divergent amplitudes, is that different from having a finite number of divergent diagrams?
I don't think so. If you take all the amplitudes into account in a given theory, then that means if you take all the divergent amplitude into account and they are finite in number, then each one of them will correspond to a graph or some set of graphs.
Now, for example, I was talking about QED. For example, we have three different divergent amplitudes there, but infinite number of divergent diagrams for each amplitude.
You mean on higher order?
Yeah.
No, okay, that's a different question. No. So right. So, okay, let me explain this. Renormalization is an order by order business. Okay? So it doesn't mean that if you have renormalized at one loop and you go to higher orders and calculate, you will get finite amplitudes. That will not happen. The renormalization count terms, these ones, if you remember last time I wrote them as a power series expansion in the coupling constant. So these coefficients must be fixed at each order of perturbation theory. So if you go to higher orders, you will need to determine, for instance, at one loop order, we determine this coefficient. At the one loop order, this is 0 in this case, we determine this. The A that we found will be proportional to lambda squared. Okay? So eventually, effectively, in this model, we have calculated this A2 by saying that A equals to minus pi prime at p squared equals to m squared lambda m squared lambda. If you go to the explicit expression here, you see that if you put p squared equals to m squared, this term of course will be finite. P squared equals to m squared will be some number 5/6 of m squared from here times 2 over lambda times 2 over eta times lambda squared. So you see that it will be some number times lambda squared. That number is A2. So this will give us, at the one loop order, this will give us A2. Okay? But it will not tell you anything about A3 and other terms. So in order to fix them, you have to go to higher order.
So we can say that, okay.
But in going to higher order, you have to make use of the information you have already obtained in the lower order. Okay? So when you go to higher orders, you have to take into account more graphs. Among these graphs, there are graphs which will be calculated using the vertex coming with lambda, the propagator, etc., etc. But you have to use the corrected vertices. Therefore, already when you go to two-loop order, this term will contribute. However, with the well-defined coefficient that you have fixed at the lower order. Then that will help you to fix A3. And when you go still to higher order, that will help you to fix other coefficients. So it's an order by order business. In this sense, it's true. There are an infinite number of graphs which could be divergent, but at each order, since we have already determined the renormalization constants at lower order, then you can determine the unknown renormalization constant at that order such that the amplitude you are calculating is finite at that order. I don't know if this was your question.
Yeah, I was saying that we can have an infinite number of divergent diagrams.
Yeah.
The theory is renormalizable. But we should have finite number of divergent amplitudes in a renormalizable theory.
Well, maybe I do not
Okay, I will ask.
quite understand the distinction between amplitude and diagram.
For example, for this this amplitude, we can have many diagrams with one loop.
Yeah.
Loops. But this is an amplitude. Anything can be here.
Yeah, but I mean, this by itself it doesn't make sense. It makes sense only in terms of these
Yeah.
expansions.
So I'm saying that this is infinite diagrams.
I guess what you mean, maybe what you have in mind is something like this diagram in QD, which is finite It's not divergent but finite, and you call this an amplitude which is finite, whereas there are other graphs, for instance, this one is divergent. Is that what you have in mind? Yeah. I'm not saying that everything that you calculate will be divergent. There are things that you can calculate is finite. In fact, this is finite due to renormalizability of QED and also because of the gauge invariance. Okay, which reduces the degree of the divergence of the graph.
Yeah.
Okay.
And can we have theories which have finite number of divergent diagrams?
We have to discuss this in the discussion session. Otherwise, it will be a dialogue between you and me.
You mean order by order?
Yeah, super normal.
So you know the answer.
No, but I'm saying I don't know any examples. I know that on the
You said super renormalizable theory.
No, I just know that
This model in 4 dimensions is super renormalizable. For example, 5 cubed in 4 dimensions. Okay, so I wanted to discuss the vertex renormalization, the Capri constant renormalization, but I think we ran out of time. So instead, let me just quickly discuss the 1 point. So far I have been avoiding to discuss the 1 point function, but we can discuss it in the time available. So 1 point function that means it is this function that we want to calculate in this model. Okay? Now, the renormalization condition tells us that that should be set to 0. But in perturbation theory, it will be given by the usual expressions. The L interaction here should contain everything, including the count terms. Okay? Whatever contributes, so you should expand this in the power series, use Wick's theorem to calculate term by term. When you expand this in power series, you see that the term which we wrote as g times phi will have 1 power of phi, and it can contract with this term. So when you expand it, of course there will be a 1 coming from here. When you expand it, it's 1 plus other terms. The 1 times phi, this is the free field phi. Its vacuum expectation value, if you write in terms of creation and annihilation operators, it will be 0. But then the next terms will have the interaction term phi cubed and the g phi in the interaction Lagrangian. The g phi term will give you I times g d and y delta Feynman x minus phi. There will be 1 phi from here and 1 term coming from I times g times phi from the interaction Lagrangian. So the time or the product of it will give you just the Feynman. But then there is also minus I times phi cubed term. So that will give you minus I lambda divided by 3 factorials. That will have 3 phi's in it at the same point, contracted with 1 phi outside. Okay? So there's a phi x and phi cubed y. Make the contractions and it will give you, I should have put the mu factor here as well, minus n over 2 plus 3, if you like. It will give you that term. And of course there will be higher order terms, but we want to go up to the lower order terms. Eventually we said that the renormalization condition is that this whole thing should be 0. So that zero will appear, will happen if G is expressed as a function of this lambda. Okay? So you see that there is a common factor here. To this order, it's very simple. The coefficient of that common factor is a constant here and the constant here. So that tells you that G should be given by lambda over 3 factorial times delta pi equals 0, which is of course divergent. I mean, I am not writing this in detail because we are not going to use it. But if you write it in the momentum space, the Feynman propagator at the origin is just this integral, and you can evaluate it. It's a simple integral, like one of the ones that we have evaluated, and express lambda in terms of this G in terms of lambda and get rid of it. And this should be repeated at every order of the perturbation theory. In the notes, I think the calculation has been done up to the end, and the expression is given for G as a function of lambda, etc. You have to do apply Fick's theorem to this. Okay? So all possible combinations. So this 3 factorial will change. Find out what's the correct number there. Is that you start from a pair action. Okay, other questions? And introduce the counterterms. The way we introduced it was to write the pair objects in terms of the renormalized objects. Okay? Now, the key point in the renormalizable theories is that the counter terms have exactly the same structure as the terms in the pair action. And the pair action was a polynomial in the fields and the derivatives. What happens in the non-renormalizable theories is that if you start with a finite number of terms in the pair action and start doing group calculation, you will see that you encounter divergences which do not have the same form as the terms in the pair action. Okay? Therefore, you will go to the action and generalize it a little bit to take care of that divergence by renormalizing some parameter in action. And then you start calculating. And when you do the calculation and go to the next order, you will see that you will need more terms to introduce in action. Therefore, you will go to your action and introduce more terms in order to renormalize. And this will continue. It will not stop. Okay? So this is the basic distinction between the renormalizable and non-renormalizable theories. In principle, the non-renormalizable theories need infinite number of counter terms. You cannot do it with a finite number of them. This doesn't happen in QED, for example. QED, the standard QED that you have seen, a very simple action. So QED has a very simple action. It's just this. There is, of course, a mass term also for fermions. This D slash is the usual D slash plus IEA slash. So that's the coupling of the fermions with the vector boson. You have the kinetic energy term for psi, the interaction term, and the kinetic energy term for the A field. And this is finite number of terms. To any order of perturbation theory you do, you'll see that it's possible to absorb infinities in the redefinition of the coupling constant, which is here, and the coupling constant there, and the wave function renormalizations. You have to rewrite the pair fields in terms of the renormalized field and introduce the analog of what we call Z. So for the A field it's called Z3, or the psi is called Z2, and then you will see the details. Okay? And then gauge invariance puts a lot of constraints and values these things. And among those constraints is that this box, famous box there, that if you count the power counting, it should be divergent. There are 4 propagators in it. In 4 dimensions, should be logarithmically divergent. But the degree of divergence is reduced due to gauge invariance, and the graph turns out to be finite. We will discuss these things. Okay? Does that answer your question? This is the basic difference. You can apply the same scheme to gravity, by the way. Gravity, if you want to apply perturbation theory, you have to expand the curvature term in powers of the deviations of the metric from the flat metric. So that by itself will introduce infinite number of terms. But the coefficients of all those terms will be fixed because you start from one single term and you are expanding it. You are familiar with the gravity action. So in the case of the gravity, the action is times 1 over kappa squared. This is the coupling of the gravitational action. I mean, the Newton's coupling, essentially. You have to start, you write usually the metric as eta if you want to apply this perturbative method that we will apply and expand this square root of g and the Ricci scalar in powers of this field. That by itself will generate infinite number of terms, but the coefficient of each term will be fixed because everything comes from here. So when you start calculating, you see that it's divergent. You will get the same kind of divergence that you get in every ultraviolet divergence. And that's the reason why it's not renormalizable. I mean, you cannot fix them. You will see that ultimately the reason lies in the fact that the theory contains a parameter of negative mass dimension. This is the hallmark of the non-renormalizable theories will be that they will contain parameters of negative mass dimension.
Do we have to submit only one question assignment on Tuesday?
Do you have to submit only one question assignment? More questions will come. More exercises will come. You want more exercises, so I will send you some more problems.